This lecture covers the last part of chapter 10. In section 10.7, we are going to talk about buffers. A buffer solution is going to be a substance that resists changes in pH when you add acids or bases. Understand that buffer solutions are all around us. In the body, we do have buffer solutions, and they absorb hydronium ions or protons and hydroxide ions that we have from foods and sometimes from cellular processes because the body needs to maintain a pH. These buffers are important to have proper functioning of cells and even the blood. So understand that the pH of the blood has to be close to 7.4, so it is slightly basic, okay? And any changes that you do to the pH in the blood, understand that affects the uptake of oxygen and it affects the cellular processes. So to illustrate how buffers work, in the illustration that we have in the slide, we have a water that has a pH meter. So pure water has a pH of 7.0. So when you add acid directly to water, if it doesn't have a buffer, you're going to change the pH drastically. As you can see, as you add acid, it's going to change all the way to 4. If you have a brand new beaker with water that starts at pH 7 and all of a sudden you add base to it, similarly, we are going to see changes in pH, but in this case, the pH is going to be increasing. As you can see, the pH meter drawing illustrates that the pH is going to change all the way up to 10.5. But what happens if we have a solution in which we have a buffer? It doesn't matter if you add acid or if you add base to the system, the changes in pH are not going to be as drastic. They are going to be close to the original pH, that in this case is going to be close to 7.0. When it comes to the components of a buffer, understand that this is why it is very important that you understand the concept of what makes something a strong acid, a weak acid, and what is a conjugate base for a particular acid. Now, as you can see, buffer solutions contain a combination of acid-base conjugate pairs. The most common of these buffers are going to be composed of a weak acid and the salt of its conjugate base. So to give you guys an example of a buffer system, we have acetic acid, and we have acetate. If you remember from the discussions that we have earlier in this chapter, acetic acid is going to be our weak acid and acetate is going to be its conjugate base, okay? You need to add this weak acid and this salt in equal amounts. So let's explore now how buffers actually work. Utilizing the same system that we had in the example of having acetic acid and its conjugate base. So when we have the buffer in the solution, we're going to have equal concentrations of my weak acid and my conjugate base. Let's first explore the scenario of what happens to the system if we add acid. When we add acid to the system, out of the two components that we have, acetic acid, which is the weak acid, and the conjugate base, understand that this acid is going to be interacting with the conjugate base. What that means is that the conjugate base, because it has a negative charge, is going to be accepting a proton from my acid and is going to be converting the conjugate base into that weak acid. So that's why we see an increase in the concentration of the weak acid and a decrease in the concentration of that conjugate base. What happens now if we have a base added to the system? When we have a base added to the system, understand that this base is going to remove a proton from the weak acid. When we remove a proton from the weak acid, that means that we're going to be forming more of this conjugate base. That's why we see an increase in its concentration and a decrease in the concentration of the weak acid. Okay? And that's how buffers resist changes to pH. Now, from the textbook, this is problem 10.53, and I want to go over, given a few pairs of molecules, can we determine if this represents a buffer system or not? Remember that by definition, a buffer system is going to be composed of a weak acid plus its conjugate base. Remember, the weak acids are not going to be part of the 6 strong acids. So if you're not in the strong acids, acids, that means that you are a weak acid. So let's look at the first example. We have NaOH and NaCl. The first thing that you should notice is that NaOH is not an acid. This is a base. NaCl is going to be a salt, an ionic compound. So by definition, because this is not a weak acid and a conjugate base, this is not a buffer system. If we look at the next example, we have H2CO3, and again, H2CO3 is not in the 6 strong acids, so that means that this is a weak acid. And if we remove a hydrogen from H2CO3, that means that its conjugate base is HCO3 negative, that when we pair it with sodium, that's what the compound that we observed here is. Okay? So it's going to be the salt of its conjugate base. So because this is the conjugate base, B is going to be a buffer system. In the next one, we have HF and KF. HF is a weak acid. KF, it's its conjugate base. Remember, if HF is an acid and it loses a proton, it's going to make the fluoride ion, that if we pair it with potassium, that's where KF comes from. So that means that C is also a buffer system. And lastly, we have KCl and we have NaCl. They are both salts So again, because of the definition that we have for a buffer, this is not a buffer system. You can also practice problem 10.54 in your textbook to determine if a given pair of molecules represents a buffer system.